You got to have that with glass too. So another problem we have with those is basically the physical size that they have to be. So the other type of magnetic field sensor we have is referred to as a Hall effect. And these guys are totally electronic. So they're solid state. And what's nice about a Hall effect, we have several different types, and I have both types up here. I'm going to get the data sheet out and wire them up for you. So we can have them that actually senses the strength of the field. So the reed switch doesn't sense the strength of the field, it just takes a certain strength to trip it, right? You understand? If you go above it, the reed switch don't know. If you go below it, it just don't work. But if I needed to figure the strength of the magnetic field, then the Hall effect would be used. In fact, what's nice about a Hall effect is when we have a type of meter, one of the meters that we have available to us is what we call a clamp-on ammeter. And the way this thing, it's got a groove or it's got a set of clamps that come into it. And what it does is it picks up the strength of an AC field. So most clamp-on ammeters do not work with DC. Because what we're doing is we're depending on what we call induction. And if you go to the motor control labs, I can see you. But what is required to induce a voltage using magnetics? Anybody know? Some of y'all have had my classes before. I know we talked about this. So if we ask questions like that, and I know some of y'all had it, and you don't answer it, what does that tell me? Well, that tells me you didn't learn it. Because if you learned it, you would what? You'd know the answer, right? So what we need to do to induce a magnetic field, and I'm trying to get it so I can get to my markers down here. There we go. We've got to have three things. You've got to have a magnetic field. And two, we have to have a conductor. And three, we have to have what we refer to as relative motion. So what that means, if I've got a magnetic field and we move a conductor through that field, it's going to induce a voltage into that conductor. Or I could leave the conductor stationary and then I could take the field and I can move it across the inductor. That's what we call relative motion. So one of them's got to move. Okay, y'all understand that? Yes or no? Yes, I am. I thought it was on. So I'm up here doing all this right. And y'all are just, thank you, Jerry. It wouldn't show up on your computer anyway because I'm writing this as we go along. So, is it coming up? So what determines the amount? So we'll go right down the list. So what would you think would determine the amount of electromotive force we produce? No, well, we're not talking about current. We're talking about EMF, electromotive force. EMF is another term we use for voltage. So we're not worried about the current right now. We're trying to see what determines the amount of voltage I induce into that conductor. We're going right down the line. Number one, magnetic field. What of the magnetic field determines the amount? Huh? We're not talking about the conductor. We're talking about the magnetic field. What of the magnetic field would determine the amount? The strength of the field. So the stronger the field, the more we get. Does that make sense? If it was a permanent magnet, you're exactly right. Well, not really. I can get big magnets that don't have a big strength. I can get small magnets that have extremely strong strength. We have these rare earth metal magnets now that you got to be careful. And them little old tiny things, and they could break the bones in your hand if you get between two. And these are little old tiny. So it's not the physical size; it's the concentration or the strength of that field. I've got some. I need to find them. I got some magnets, and they're little old tiny things, and they come off a disk drive, and it's really, really hard to get them apart. These aren't too bad. Here they are. So these are what they refer to as rare earth. Look at the size of these and look at the size of that. These are two of them put together. Here's one. Somebody come up here and get this and try to pull this apart. So this would induce a lot more voltage than that because it has a what? It has a stronger field. Well, these you can. Now, all we're trying to do is we've got some very small, maybe 5 millimeters across. They're pretty dang strong. Now do the big ones. Be careful though. No, so you can't say the physical size. Understand that it's the concentrate. How good does those things concentrate that field, or the strength of the field? Now you said it a while ago, Jerry. What we do is we know in electricity, if we put DC voltage sources series 80, and this is 3 volts and this is 3 volts. If I measure across, I would measure 6. So what we do is we start looping this wire in the same direction. So if this right here gives us, 1 millivolt, and this one right here gives us 1 millivolt, if they're in the same direction, then all the voltages would be additive for the direction of the current. So what we say is the number of instructor loops or coils and they have to be in the same direction. So you can't coil it this way and turn around and coil it that way because they would, that would be series opposing. So the strength of the magnetic field, the number of conductor coils, and then what would number 3 be? About motion. What can I do with motion to get to adjust the?
Please back up there.
Yeah. Motion. What would you think would determine the amount? Well, we're talking about that controls the amount, and you're saying the same speed. Well, if I run it at the same speed, and I don't change, yeah. So the speed of the motion. Good. So now you understand how an alternator works, and you understand how. So you're out there in your car. And that's what you're doing. You're spinning a magnetic field. And you're spinning it across coils of wire. So when your car goes faster, your alternator tries to put out more voltage. When your car goes slower, it tries to put out less. So how can I make it put out the same voltage all the time? Huh? Yeah, but how does it work? What does it do? How does it regulate the voltage? You're not out there rewiring your alternator, so you're definitely not changing the number of coils, right? And your motor is changing speeds all the time, so that's what we're trying to compensate for. We're trying to make our alternator put out the same voltage whether I'm going 100 miles an hour or if I'm sitting there at a red light. Huh? Your car runs at a constant motion? Does your car, do you always go the same speed? Okay, so we don't adjust, we don't regulate with speed. You don't get out there and you don't rewire your alternator, so you don't regulate with the number of coils. So there's only one thing left. What can we regulate? What can we change? I can't change this. I can't change that. So what can we change? Strength of the magnetic field. So we're not spinning a permanent magnet out there. We're spinning an electromagnet. Y'all understand electromagnets? I got one in my bag. I can go get it and show y'all. So we got an electromagnet that what can we do with an electromagnet that we can't do with a regular magnet? You can control the strength of the magnet. So that's what your alternator does. I mean, that's what your voltage regulator does. What does it do? It sits there and monitors the output. If the voltage tries to go up, it decreases the strength of the spinning field. If the voltage tries to go down, it increases the strength of the magnetic field. So now we know how, huh? Well, not 12 volts. It's probably around 14, it's a little over 14 volts. Lead acid batteries are we call it voltage charge. So to charge a lead acid battery, you have to put more voltage on it than what it's, okay. So usually when your car's running, if you put it across your battery, you're going to measure about 14 volts. A little over, about 14.3. It's usually a fraction there, but it's going to be 14 volts. And that way it will charge all the time. Your engine's running, it's setting it. Well, what you mean? Voltmeter? Well, that's. Yeah, what we have to do to get, so we got a magnetic field. It's electromagnetic field that's spinning. And of course we got a north and a south pole. And we got to get current to that thing. So what we have is we have something called a slip ring. And if you ever looked at the back, it would be two copper rings. And then we have what they call a brush, which is a carbon unit, and it comes in and runs on these slip rings. So these slip rings are spinning, and of course this is sitting on the slip rings, and it allows us to put DC current into the rotating coil. So an alternator will wear out. Y'all understand that? Either the slip rings are going to wear out or the brushes are going to wear out. Usually the brushes wear out first, and that's why they want you to trade these things in. Because these guys, they're built so sturdy, odds are you're not going to burn up the coils. What wears out is either the slip rings wears out or the brushes wear out. So what do? They go in there and replace those brushes. I had mine go out. I had a big old Dodge van, customized van, and my alternator went out, and I bought the brushes, and it cost me $2. And I replaced them myself. You go out and pay it. I don't know what the rings are. I would compare the brushes. Well, the rings, the slip rings, we call them slip rings. They are mounted on the back, on the shaft of the rotor, and this is the way it transfers energy from the brushes to the rotor. We call them slip rings. You got them on your steering wheel. So you're sitting there spinning your steering wheel all over the place. And how in the world can you have speed controls and horns and all that other kind of stuff if your steering wheel is moving? Well, if you ever took a steering wheel off, you'd see all these little old tiny fingers that set up there. And then they got these copper rings down there. We call them slip rings, where it can transfer stuff from a rotating thing over to a stationary thing, right? So your steering column don't move. So you know they don't have wires running through your steering column going up to, because you'd be spinning those wires and you'd be twisting them up all the time. So that's the way we transfer information between your steering wheel and your body control module, right? We do that, and of course alternators have the same thing. So we got to have the ability to go from something that's, we got to have the ability to transfer stationary, something that's stationary over to something that's what? Rotating. And not only rotating, we're talking about rotating multiple times, right? You understand? So the primary method to transfer DC is through something called slip ring. We call them slip rings because that's what's happening. These brushes are what? Sliding or slipping across those rings. So yeah, if you ever took a steering wheel apart, you'd see that. You know, if you got all these controls, and we're putting more and more controls on our cars now, right? What can you do from your steering wheel now? You can change the volume of your radio. You can change stations on your radio. You can engage your cruise control. You can disengage your cruise control. You know, some of them you can adjust your mirror. Yeah, some of them you can answer your phone on your steering wheel. But they got to transfer it from your steering column, which is stationary, to what? To that rotating steering wheel, and so we use slip rings. So you just hadn't seen them. They're in there, I guarantee. Well, I mean on your alternator. So you've never had your alternator part. So you can slide the brushes out, and if you look down through there, you'll see. If you look down in the hole on the mount, it's got a little plastic mount in there. You can see those copper things. So yeah, if you change those brushes are riding on slip rings. No, the brushes have the wires going to them. So the brushes have the wires going to them, and then they got a spring. And of course, the function of the spring is to keep tension so those brushes ride on those slip rings. But this end right here, this is the working end. These are the guys that's actually riding on the slip rings over here. The only way you can see them really is to take the alternator apart. If you all just pull those brushes out, they're still hard to see. You can see it. And now, of course, over time, these things are going to wear out because it's things rubbing together. Anytime you see things rubbing together. But on most alternators, they're replacing. Huh? Oh, yeah, that's what I was saying. We was going, huh? No, I haven't did the slip rings, but yeah, you're right. You got to hold the brushes. You got to hold the brushes back, especially depending on how they mount. So what we have now is your more expensive clamp-on out meters can. So if I'm going to measure, and what if I'm putting. So what determines how much current you can get out of an alternator? The size of the wires. You'll understand that. The gauge of the wire. If I didn't put a load on it, I mean, I could use 24 gauge wire and I could spin it through a magnetic field and I would get a voltage. But if I tried to get current through it, all that resistance in that wire would drop that voltage. So what determines the amount, of course, is the gauge of the wire, how big the wire is. So if you look at a high current alternator, you'll see it's got a lot of turns, and this is why they take up so much space, because if the gauge of the wire is bigger and you got to have 500 coils of wire, right, you understand, or more than that, then the alternators and stuff are going to have to get bigger. So a lot of people say what determines the amount, and people want to say the size of the wire. But we're not talking about current, we're talking about voltage, right? You'll understand the difference. Yes or no? So we can induce a voltage into a wire, but we got to have three things. We got to have a magnetic field, we got to have a conductor, and we got to have relative motion. So this is the way a transformer works. So a transformer only works on AC. So anytime I put current through a wire, it creates a magnetic field. Y'all understand that? But to transfer that to another coil of wire, we got to have motion. So a transformer only works off AC because AC generates a magnetic field. We can have a bunch of loops of a conductor, and the AC automatically creates motion, right? You understand? Because it's constantly doing what? Changing direction. So that means I can come over here and put another coil of wire over here, and when this changes over here, it's going to induce a voltage over there. And the amount of voltage I get depends on the ratio between this and this. So if for every 2 turns of wire over here, I only had 1 turn, then this transformer would divide by 2. So now we've got a means, since we have everything we need, we have a magnetic field because the AC's putting current through it, right? We have a bunch of coils of wire inside the transformer, and we've got motion. AC generates motion. So that's the way transformers work. You know how a transformer works. Well, so well we could change the ratio. So over here I could put, for every 1 turn, I could put 2 over here, and now the transformer would step the voltage. It would multiply the voltage. So depending on the ratio between this guy, which we call the primary, and this guy, which we call the secondary, the ratio between those two determines the voltage that the transformer sends over. Well, anyway, so if I'm going through a system and I'm doing this right here, right? You understand? Then everything that points back toward the source, every coil that points back to the source, I don't care how many you go to, they are the primary. Every winding that points toward your house is the secondary. So in a transmission system, we have multiple substations. We call them substations. And of course, this is in there to step the voltage up for transmission, because we're not trying to give you voltage. We're not trying to give you current. We're trying to give you power, right? You understand? And the higher we make the voltage, the less current is required in the transformer to produce that power. So we can step the voltage up extremely high for transmission, and then we step it down for safety. You understand that? And we can do that with transformers. So that's why AC is the predominant method of transferring, distributing power, not voltage, power. They don't call them voltage transmission lines. They call them power lines. Your company is called a power company, right? So we're not saying, and the higher they can transmit that voltage, the less current that's required. And then, but we have to start stepping it down because, 750,000 volts, you have to put that stuff, 60 feet off the ground or something like that. Y'all see some of these big high tension lines, they're way up there. So that means if I'm going to measure this, the amount of current I put through there gives us the strength of the field. So if I can come over here and I have a conductor and I can put a bunch of coils of wire around it, then the amount of EMF I get out of here would be directly proportional to the current flow through the wire. We call these CTs, or current transformers. So we can measure current indirectly without ever breaking the wire, but we don't call these ammeters, we call them CTs, current transformers, or we call them clamp-on ammeters, which is nothing but a CT that's mobile, so you can break the coil and put it across them. But these guys only work with AC because to induce a voltage, you got to have motion, right? You understand that? So anybody says we can measure current with a clamp-on ammeter, that's not exactly true. We're not measuring current. It measures the strength of the field. But the field is directly proportional to the current. But it takes a lot of magnetic field. So usually when you look on these clamp-on ammeters, the smallest current range on that's like 40 amps. So if you put it across a signal that had 200, 2 volts of AC, it's going to measure 0. But what if I need to measure DC current? Then we've got another device called a Hall effect that measures the strength of a field. It does not depend on motion. It literally measures the strength of a field. So we can get clamp-on ammeters that's got Hall effect in it, and there'll be one that tells you that it measures both the clamp-on measures both DC and AC. Now these are going to be the guys that cost a lot of money, right? So you go out there and you can buy a clamp-on ammeter for $65, and over here, this guy over here is $300. You wonder what's the difference? Well, odds are that $100 one is going to have a Hall effect, and it's going to be able to measure DC and AC just by clamping it across the wire and not doing what? Not breaking the circuit. I wish I brought mine over here. We got one, but it's over in the motor controls lab, and I didn't get over there. So a Hall effect but it's digital, it's a solid state, right? You understand? A Hall effect sensor will measure the strength of the magnetic field, and it's a DC field. Strength of a DC field, let's rephrase. If you put an AC field out there, it would just cancel itself out. But we can combine the two in a clamp-on ammeter. I need to talk to you, Brittany, before later. Nancy wants me to ask you something about your locator card. Have you done? Okay, gotta be done. So we got a couple up here. Huh? About the charger. This is mine. I brought it from mine. No, I didn't rip you off. I brought this with me. We got the same computer. So one thing, the Hall effect is, if I look, and this is the way we can tell the difference right off the bat. First of all, what they do is that when we look at diagrams, we're going to see this diamond shape right here. And this is the shape. When we see this means this is some type of non-contact sensor. And normally they'll come over here and they'll put two lines. And this will be where we control the power flow. And then they'll come in and put the symbol of a switch in here. Like that. And this is what we would see for a Hall effect, because a Hall effect does not have to be powered up. No, I'm sorry. This is what we'd see for a magnetic reed switch, because it does not have to be powered up, right? You understand? What we do is, of course, this would be L1, and then let's say we had a light bulb over here. Well, if it's an electronic sensor or a sensor that's required to be powered, then what we'll do is we'll add another wire coming out the top, and it'll come over here and connect to L2. So if you see one of these, you know it is probably a solid state sensor, an electronic sensor, because electronics do not work unless you power them up, right? Y'all understand that? Now we do have a couple of sensors that require such low current it can power through the load, and we'll look at those in a minute. So it means if I'm looking at, and then they'll put another symbol in here that we'll look at that tells us what that sensor is. So I think this right here is a sensor for a magnetic sensor. So it means if I'm looking at a diagram and I see the symbol that indicates magnetic, and it's only got 2 wires coming into it, I know it is a reed switch. If it's got 3 wires coming into it, I know it's a Hall effect. That makes sense? Yes or no?
So 3 wires is a Hall effect. 2 wires.
2 wires is a magnetic reed switch. because the magnetic reed switch does not have to be powered up. Y'all understand that? Yes or no? We okay?
I was thinking of the reasons we had to,
They didn't have to be powered up.
line.
They have to be in line, and this is what the symbol is. So they got to be in line, and they got, of course, what we do. Remember, in motor controls, we have basically two sections of a line. Between L1 and the load, this is where we put our control devices. We put those over here, and then over here, and decision making too, by the way. And this is where we make all our decisions. So we make two things over here. And then over here, this is where we put our what? This is where we put our loads, our relay contacts, our solenoids, and stuff like that. So here's our sensors. So our sensors have got to be, and of course, how many sensors can we put between the load and L2? They can be in parallel, they can be in series, they can be in series parallel, because these are decision-making devices, right? Okay, y'all understand that? And then loads depend. So in control circuits, we don't have series parallel circuits. You say, well, those contacts are in series. But when you learn about series parallel circuits, we're not talking about control devices, we're talking about loads. So when we talk about a series circuit, that's multiple loads in line with each other, right? You understand? Of course, in controls, we don't have series circuits. We have single element series circuits. So we have single element series circuits, and then we can put multiple loads in parallel. So all we have is single element series circuits, and we put multiple loads in parallel, right? Y'all understand that? And this is motor control. This is controls. And this is also true when you get into PLCs and stuff like that. And of course, one circuit between L1 and L2, so the entire circuit, what do we call that? A circuit that runs between L1 and L2, we call it a rung. And each one of these, we call this a line, right? So this guy here, so a diagram could have multiple lines in a rung, but we can only have one load per line. We can have a lot of loads per rung, but the loads have to be in what? They have to be in parallel. So a circuit between L1 and L2, we call it a rung. And of course, we put multiple circuits. So every circuit is called a what? It's called a rung. They could be a single element series circuit, or they could be a multiple load parallel circuit. But we don't put loads in series. But we can put contacts in series, because that's not what determines if it's a series circuit or parallel circuit, right? So what we're saying is, yeah, it's got to be in line with something. But so I'd come over here and do this, and then I would come over here and I would put whether it's a normally open or normally closed switch. And then down here, I would put the symbol for a magnetic sensor. So that's one thing we're going to have to learn. And this right here would be a reed switch. Now, why would it be a reed switch? So this right here would be a magnetic reed switch. And this over here would be a Hall effect. Now, what's the difference? Well, the Hall effect is electronic. It's got to be powered up. It's got to have a connection between L1 and L2. The magnetic reed switch does not have to be powered, so it's not going to have that third wire. So any wire, any sensor that requires additional power, it will have three wires coming into it. Any non-contact sensor that don't require additional power, that powers up through the line, then it's only going to have two wires. That makes sense? So this is the way we tell them. And one of the things we'll do that we're going to have to get in today is start looking at these symbols. Because we have a lot of non-contact sensors. Now, The only contact sensor we have so far is a limit switch. So limit switches are not inside this diamond shape. They'll be drawn with the symbols that you learned. They'll be drawn with the symbols that you learned in motor controls. So if you come up here and see that diamond, it's going to be a non-contact sensor. You know it's a non-contact sensor. And then it's going to put a little symbol down at the bottom of the triangle that tells us what type of sensor it is. So magnetic sensors have little symbols. Photoelectric sensors have little symbols. Y'all understand that? There's symbols in one of the PowerPoints that we have. Yeah, it's up there online. The PowerPoint should be up there. And we're going to have to get into that because we're going to spread this review over. So when we get into looking at diagrams, we'll get a basic feel of the rest of these sensors. But we're not going to get to them in a lot of detail right now. We'll just say, okay, what does this sensor do? Well, this sensor senses metal. Well, this sensor senses solids or liquids. Of course, we know what a Hall effect and we know what a magnetic reed switch does is they sense magnetic fields. The magnetic reed switch will not tell us the strength. Now, normally all the magnetic reed switches we have available to us over there, these are digital. So they're not going to give us the strength. They're either going to open or they're going to close. So they look a lot like a reed switch, or they're going to do the same thing that a reed switch is, but they're going to be able to be a lot smaller, right? You understand? And plus they last a lot longer too. So when we come up here and look at a reed switch, so here's, I think I hooked up my camera. No, this is not the one I want to use. Let me turn this off. I got another camera that I use. This one's okay though. I can do this in full screen. So we got both of them over here. We have, and I don't have it wired up, and we'll take a little break here in a minute so I can look up the data sheet and see how to wire them up, how to put power up to them. Make sure I put the power up to the right leads. But this is a Hall effect right here. And we see 3 wires. So between 2 of them, it's going to be the switch, and the third one is going to be for power. And that's what I got to look up. And look at the size of these things. Yes, can't you see the 3 leads coming out the bottom? This gets, you got to see one. You can see the 3 leads coming out of here. Okay. And we have 2 types up here that we're going to look at. That's why we have 2 of them hooked up. We got this guy, and we got this guy, and my LEDs are gone too, so I'm going to have to come back. So what we got is we got an LED that we're going to hook up. And we'll come in, and then we'll power it up. Oh my goodness. This one don't have a number on it. So I have to figure out what it is. This one's got the part number on it right here.
You said that's Hall effect.
Yeah, these are Hall effects. What do you mean?
I mean,
Yeah, this is a resistor. If you've got something that closes, and you're trying to put it across the line, you got to have a load. So here, instead of us using a relay or something like that for a load, we're using a resistor for a load. So both of them's got resistors in there. So this is the actual load that we're going to be switching either off or on. Understand, Jerry? So I've got to have a circuit. So these guys are acting like a switch. So what that means is if they're acting like a switch, and I come over here and do this, what have I got to put over here? I got to put a load because if I just put it between L1 and L2, I got big problem. So what we're doing here is we're using a load. We're using a resistor as the load. And then, now this is solid state, so there is not a switch in there. It's a transistor in there that's acting like a switch, and it's an electronically controlled switch. Where in a magnetic reed switch, there is a switch in there. It's a mechanical switch. There is absolutely no moving parts in this. So the switch itself is a transistor that operates as a switch. So what's nice about a transistor is we can operate those things like a switch, but instead of being mechanically, they're switched what? They're switched electronically. So if I look at the diagram for it, which I think I still got up. I thought I did. Let's see. Oh, there you go. Then they would show you this is a switch, or this is what we call a latching one. It's pretty interesting. But here's the layout right here. Here's the actual output. This is the electronically controlled switch right here, called a DC transistor. Notice they got this. So I put my load right there, and this thing output is electronically closed. It's not a switch, but it electronically creates an extremely low current path between these two leads right here. This we call the collector. This we call the emitter, and the current would flow up through here. But if I don't put that voltage right there from the output, this thing acts like an open switch. If I put an output of this thing, that output driver, then it acts like a closed switch. Unfortunately, it's not a closed switch, and it's not an open switch. So these guys here will always drop a voltage. A true closed switch, if you close it, it'll drop 0 volts. But a transistor never can drop 0 volts because it is not a closed switch. So we have what we call a saturation voltage. When you take the sensors class, or if you take the sensors class, we have about 2 volts across these things, or usually less than a volt. The ones we have that run off 120 volts AC, those things drop about 1.4 volts. But you got 120 volts you're working with, and you drop 1.4 volts, that's nothing. You get down to 5 volts or something like that. So these sensors, I don't know what the voltages are on them. I think they got a wide range of voltages we can put on them. Yeah, so this thing will operate anywhere from between 2.4 volts all the way up to 26. And then it says, okay, the different currents and all that kind of stuff. But we'll go in and look at this. As soon as I figure out how to power it back up and how to hook up my LEDs, make sure I do it right, then we'll do that. So my output pin is pin 3. All right, let's go ahead and take a break. So let me make sure I get the pins right. I think they run from left to right, which is pretty common. So 1, 2, 3, they run from left to right. So pin 1 is VDD. Pin 2 is like rainy days, it makes your tin shoes squeak. Believe me, I understand. I know I've saved these things somewhere. I don't know if this one looks like it's powered up too. All right, y'all guys, y'all come up here. It's a lot better if you see them than you see it through a camera, right? But I'll go ahead and record it too. So, using our data sheet, just using how to hook it up. I think I closed it out. Then here's our LED. Here's our resistor. So LED, when a diode is what we call forward bias, you have to protect it because it acts like a closed switch. So the resistors in here is in there to drop the voltage. The difference between the voltage drop on this guy and the voltage drop on that one. Also limit the current. And so here's the magnetic field. And the way this thing works is so one polarity turns it on, and it holds it, it latches it, and then the other polarity turns it off.
That little bitty black thing's essential. Go figure.
Yeah, but look, so I can come over here and approach this from now. I'm sorry, I moved it a little bit. But see, I can come into the same pole all the time and it don't change. So what actually is calling this is what we call a latching Hall effect. So it's going to hold that until it sees what? The other pole. Now the way this works on the way it works on the sensor is here. It's got a magnet inside on the piston, right? I understand. And so what happens is when it moves this way, it sees one field. Then if we move it back, it sees the other. Did that? So now this is the proximity sensor. I need to turn it the other way. So here comes my piston. It hits it. What does it do? Turns it on. And then when it moves away, it sees the other field and turns it off. So this is the way those sensors are working over there. Now this is what we call a linear proximity sensor. Where's my meter at? So hopefully it's wired up. I didn't look at this one. I just found it. So a linear Hall effect should give us a voltage that's proportional to the magnetic field. So the closer I get to this one, the more output we're going to get, or vice versa. I don't know how it should be. It might be lower. But what we'll do is we'll come over here and get a couple of wires to hook up with a meter. These guys here, by the way, are named.
You folded them up so neatly a while ago.
That's okay. I've done it 100,000 times. So this is our series drop-in resistor. So it's hooked up between here and ground. So when you measure the voltage drop across this resistor, this should give us, and this should vary with the strength of the field. So now supposedly if I get the magnetic field closer, it should go up. I just see that. Yeah. And if I go it down, go away, it should go down. I think if I approach the other polarity, it'll actually go negative. Let's see, so this guy right here is actually measuring the line. Yeah, so if I put it on this one, if I approach it with this pole, okay, see that? Oh, I touched it. So we can use these guys to measure the strength of the field. This guy is a latching Hall effect, and all it does is when it latches, it stays on until it sees the other magnetic field, right? I think. Yes or no?
Or it doesn't see any field. That's the other magnet.
Well, it does. It sees the other field. So one field turns it on, the other field turns it off. And of course, you can see it if I come in like this. So now I can come up here from now to doomsday. So if I can come up here to now to doomsday and it don't change, okay. And I can take it off and it slaps, right? And then when I flip it over, as soon as I get up there, it turns off. I'm trying to see it. So off, on, off, on, off.
Well, you were sliding it down.
Well, that's what we're doing. So you got to understand the way the magnet works is that if we move it, the magnetic field comes in here and it comes in there, right? So what it does is it sees, see the way we hold the magnet, right? So so you got to imagine on that the cylinder that magnet is looped around. So that would be like me coming from this side right here. So what we have is we have the field moving in different directions depending on which side I come in, right? So what we're saying is if I come from this way, yeah, then it comes off the other one. So what we're doing, if I come in from this side, here comes my piston, and it hits this, and then it comes on. And then when we go away, which is the piston's going to do, it's going to turn off. So this is what these guys are using over here. They're using this guy right here. And then you can see that piston coming in and turn. Now the LED would come on, right? And okay, and then when it moves back off in the opposite direction, it'll turn off. So here, if we approach it from this way, it turns on. Sorry, if we approach it from this way, it turns on. If we go away from it in the opposite direction, it turns off. And these are the way the Hall effects work over there. And we'll look at the diagrams in a minute, and we'll see. So they don't use these over there because all the Hall effects over there are used to either say the piston's there or the piston's not there, right? You understand? But what's nice about these is they're going to be fairly small compared to the reed switches. The biggest disadvantage, of course, is they've got to be powered up to operate. So that's right. We got this power supply over here that's powered up the Hall effect transistor. So that's why we got to have 3 leads. 2 of them for power and one of them's common. Then one of them's for power and the other one's for signals. Okay.
Well, this is your common, this is your...
Well, this is my ground. It is common, but it don't have to. These are isolated power supplies. Notice these are not labeled. These are not labeled ground. These are labeled common. And this common and this common are completely different. So if I wanted to use both these power supplies, then I would have to run a wire between here and here. If I want it grounded, and there's a ground terminal back here, then I would run a wire between here and here, and then that would reference the power supply ground. So this is an isolated power supply. Well, they call this common, but is it common? Well, I don't know why they call it that. I wish they would have named it plus and minus.
Well, you can take a marker lot.
We could, but you understand the voltage is relative to what I use for common. So I could use this as the power lead, and I can use this as the common, and I would have a negative power supply because they're not referenced to anything, right? You understand? So when we start looking at the PLC, the power supply of the PLC, they don't reference any one of them as common. They say plus and minus, and then it's up to you to determine what is common, right? Don't understand what we're saying? Yes or no? Yeah. So this shouldn't be labeled common. This should be labeled what?
That'd be plus.
This should be minus, and this should be plus. And this right here should be labeled 0. It should be labeled
black one.
Yeah.
Oh, okay. Yeah.
But we don't have that problem here. This is a good common because on this one, I have both a what? I have both a positive and I have a negative supply. So this is okay. This over here, this one right here is the one that's not quite right, because this one right here, I can get a -5 volts by using this as the common, or I can get a +5 volts by using that as the common, right? So this is on the common. This right here is right, because over here we have both a what? We have negative and positive supply. So that was it. And neither common is, these commons are not together. So that's something we have to remember. But now what's nice is they're totally isolated from each other.
We're not gonna really use that.
You should. I mean, it's a good thing to learn how to use. Now the trainers are grounded. So the common on the trainers are grounded. So we got to be pretty careful on that. But that's neat. So this is a linear Hall effect. This is a switching Hall effect. But this is actually latches. So it actually latches until it sees the field move in the opposite direction, or if we swap fields. So what it's looking at is if we're moving the field this way, or if we move the field that way, right? And it sees a different, see, and that's what they're using over there. They're using these switching Hall effects. But look at the size of them. And they could be smaller. It's just that they have to make them big enough for me to handle. Okay? All right. So we can go over there now. Let's go over there and well, let's look and see the diagrams. So I'm gonna get out of this PowerPoint right here. Go to the. I don't have to get out of it. I can just do another one. So we'll leave this one up, and we'll come up here. And my taskbar is not popping up. Huh. My taskbar is not popping up. Oh, I know what's going on. This camera takes control of everything. This is a good camera. It's got a really good resolution on it, but it updates so slow. So this is pretty standard inside this, and this is the distribution station. I don't remember what they call it. That's what they called it on the Festo line. We'll go over that in a minute. So, and I'll run this off for y'all. So anytime we see A, it's going to indicate it's an actuator. And what's an actuator? It's a device that takes a power source and converts it into motion. So we have two types of actuators. We have linear actuators and we have rotary actuators. B, so if we see B on the drawing, it indicates it's a what? Sensor. H indicates it's a indicator lamp. K is used for what? Relay. I'm going to give this out to you. chugging. M is used for what? Solenoid of a directional control valve. Y'all understand solenoids? Everybody okay on solenoids? Everybody okay? What's a solenoid? And of course, I turn my camera on. They won't see too long to get it back up. But that camera takes control over everything. This is what I want there. And I think I had 2 versions of it running. So this is a typical solenoid. This is pretty big. And we have AC solenoids too, by the way. And they things have not been working for me today.
You said actually
An actuator does not turn, it takes a power source and converts it into a motion. And we have 2 types of actuators. We have linear actuators, which are going to take a power source and convert it into a straight push, right? And then we have rotary actuators, which are going to take the power source and convert it into a rotary motion. And now the camera is not even showing up in my task of select cameras up there. So let's try this other way. Then it says it didn't check my camera, even though I've used it. Let's try this other application and see if it works. This right here. So this is a pretty typical solenoid. This is pretty easy to understand. They can make these all different sizes. But what we do is we have a bunch of tons of wire, and then we come in and we put a metal rod into the wire. Then what happens is when I put a DC current, this is a DC solenoid. We have AC solenoids too. This is a DC solenoid. But we come over here and we put current through the coil, it creates a magnetic field. Magnetic fields attract metals. And then what happens is nothing. And it should work off the 5 volts. If it's not, I'll move it over to a bigger power supply. So it needs a bigger, let's see, when we put that power on there, what does it do? Okay. So on this end right here, of course, it pulls it in it, and I could use this side right here. I need higher than 5 volts on the thing. So I'll turn the power supply off. And normally we have a spring or something to return the solenoid to itself. So a solenoid uses electrical current to create a linear motion. And then when I turn this off, a spring back here would do what? We'll push it back out. And this is a solenoid. And we lose, this is the main element of a relay, solenoid. But what we do is we use solenoids to push that spool inside the directional control valve. So the Amateur line puts together a directional control valve, but it's what we call manually operated, right? We saw that thing's got a spring. Well, if I can push that spring in and cause that spool to move, then I can use a solenoid to cause the spool to move. If I use a solenoid to cause the spool to move, then we can control the valve electrically, right? You understand that? So every one of the directional control valves over on both the lines, those are solenoid operated valves. That's all a solenoid is. If you've got a washing machine, what turns the water on and off? Solenoid. Yeah, so if that plunger went in there and plugged up a hole, when we energize it, it would let the water through, right? You understand? And we de-energize it, the spring would turn the water off. Ice makers work that way. Some water fountains work that way. You got a little old tiny button on, instead of pushing these big old things in like they have here, those are manual operated valves. If you got a little old tiny button you push on the side, it's probably a solenoid in there turning the water on and off. Your washing machine definitely works like that. So you got two on your washing machine. You got one on the hot and one on the cold. That way it can control. So if you look, there's a big plastic unit down there. It's got 4 wires hooked up. It got 2 solenoids back there. So we represent the solenoid. If we see this thing right here, if it's an M, it's going to be a solenoid that controls the valve. Everybody okay there? S is used for what? Switch. V is used for the valve itself. Everybody understand? Yes or no? And then Z means it's a pneumatic service unit. Y'all know what a pneumatic service unit is? Yes, no? Huh? That's where the regulator's at. That's where the filter's at. So a service unit has multiple devices. So those gray knobs we push, that would be the regulator. The disconnect would be part of the service unit, and the filter would be part of the service unit. Are we okay so far? Like I said, I'll run this up to you. So this would be the example of the first station. So our 2 solenoids, our 2 magnetic sensors are called 1V1 and 1V2. And we'll look at that in a minute. The flow control valve, it's a valve, it's called 1V2 and 1V3. This sensor down here, this is a photoelectric sensor. It's V1, so it's a sensor, right? You understand? Are we okay? Now, when we look at the drawing, these are the pneumatic symbols. And I can't print right now. For some reason, I can't map this printer. So this is the symbol for a pressure. This is a sensor for a service unit. And basically, this is the filter symbol. This is the regulator filter. Symbol. And this is the symbol for a gauge. But notice it's all inside this dashed line, which means it's what? That means it's all in one unit. Okay. This is a symbol for a pressure switch. So if we see a square with a P on it, it's a what? This is pressure switch. This has an analog output. This is a sensor of a pressure regulator. This is a symbol of a digital pressure sensor. This is a sensor of a one-way adjustable flow control valve. Do y'all understand that? Huh? Some of y'all do. Some of y'all had pneumatics. You had pneumatics? Oh, heck, y'all set up. What we can do with this is that when we control the speed of the flow, we don't want to control it on both the exhaust side and on the pressure side. So what we do is we control it on one side. and we bypass it on the other. Y'all understand that? Yes or no? Huh? I don't know if that's in this one or not. I think I closed it out here. And when the camera's working, my taskbar won't pop up. So we're through with the solenoid anyway. There we go. So we have two ways we can control this. Oh, it's up and running. It's up. So what we do, so this is the symbol of the directional control valve. How many positions does this valve have? Got this block over here, we got this block over here. So how many positions? It's got two positions. It's got 4 ports. The number of ports it has we call ways, and the number of positions we have we just give a number. Unfortunately, the way they do it, they do the ports first, then they do the position second, and then they use the term way. So we call this a 4-2-way valve. And this is the symbol of a solenoid. Yes, but we don't say 4-way 2 position. It's strange the way they say it. The way they nomenclature, when you look up, when you're ordering these things, or when they look them up, they say the number of ports first. Then they say the number of position, and then they use the term way. So this would be called a 4-2-way valve. That's what it's called. But it has 4 ways, 2 positions. But its nomenclature kind of strange, right? 4-2-way valve. So that's what we call it, 4-2-way valve. And what we're doing is we're using the solenoid. So right now, this solenoid will be energized and it pushes the valve that way. The red is the flow coming from our service unit. It goes up. Where does it go? Well, it goes through the check valve. So that's the way the check valve works. It's a V and it's a ball. So if I put pressure on the top, it's going to push the ball into the C. If I put pressure on the bottom, it's going to unseat the ball, right? Understand? So what happens is that when it goes in there, it's going to bypass that one. Now, of course, what's going to happen is the cylinder is going to move this way, right? You understand? And then it's going to force air out here. Here, the air's coming this way. It's got to go through the flow control valve. So the flow control valve is going to control the speed of the fluid. So flow control valves do not change pressure, they change flow. And of course, what does the flow, the pressure determines how much force we can generate. The speed of the flow determines the speed the actuators move as a result of that pressure. Now, the problem with pneumatics is that if we got a compressed air and we push it, then what would happen is when the cylinder moves, the air would uncompress. And then it has to pressurize again. So what pneumatics does is that we do what we call meter out. We put our flow control in the exhaust. So the exhaust, so what we're doing is we're pushing against something, right? You understand that? Right? So what it does is it makes the cylinder move a lot smoother. So if you put your flow control in the exhaust, we call that meter out. If you put the flow control in the pressure, we call that meter in. So pneumatics, the standard way to control the speed of a pneumatic is to meter out. Because if we didn't, the cylinder would be real jerky, right? You understand why? Yes or no?
Yes.
And of course, hydraulics, it makes no difference. So hydraulics, you can meter out or you can meter in. But the rule of thumb is when in doubt, meter out. So the standard way, huh? Can I what?
You know, these numbers over here. You can't sense that.
What do you mean says what?
Well, as this breath, you're adding more air or whatever.
Yeah, but what would happen is,
Pushing it out, okay. So what you're doing is you're setting that control valve where it ain't gonna exhaust.
right, and that what had happened is now we're pushing against a pressure. So the valve, the piston moves with the flow. If we got it on this side and we metered the other way, when it pushed it, it would uncompress. And then it have to compress again. Then it push and it uncompress. Because we're not pushing against anything, right? So what happens on pneumatics, we meter out because that way the cylinder moves smooth. If we metered in, the cylinder would do what? It would jerk. That's why we meter out. And hydraulics works either way, but the best thing to do is just meter out all the time, and that way you won't say, well, is this hydraulics or is this pneumatics? And that's what the expression goes. It says, when in doubt, do what? Meter out. So when we put the flow control in the exhaust or in hydraulics, we call it in the return line because in hydraulics, we have to bring the fluid back to a tank. We don't call it exhaust, we call it return. That's one difference. We can meter either way.
That's why you got two control valves.
Yeah, so that's why we got one control valve. And what's nice about this, and this gives people trouble, is visualizing what happens. So we draw the valve is drawn in its original or initial position. So that means when we go over here and turn that thing on, those valves are going to be in an initial position. So we draw it in that position. And then what you have to visualize when you visualize this flow is you have to visualize that whole symbol shifting. So I did this graphic myself. So you can see when 3M1 energizes, it pushes that whole thing over, right? You understand? And notice what happens now. Now the pressure comes up through this. Since it's pushing, it goes through the check valve, comes through, pushes the cylinder this way. This exhaust now it can't go this way, so it's got to go through the flow control back to the exhaust line. And this is we call this guy a manifold, and this is very popular. So instead of run pressure and exhaust, all of them's got to have pressure and all of them's got to have exhaust. So what we do is we share this in a manifold. So we put a manifold out there, and now all the valves just mount on the manifold, and they pick up the exhaust and the pressure through the manifold. Festo does it unique. Amatrol does it the way I've seen most often, but Festo is really neat. We'll go over and look at that. But what you got to visualize is when these solenoids are energizing, that whole symbol does what? Shifts. Now we can't shift it on a static, and this is what a flow control valve does. A flow control does not change the pressure, it changes the flow. So it's just like your water hose. It's a bad feel because the water hose is so springy, is that you can go out there and turn that little old valve on just a little bit, and if you put your hand over that, you still can't stop it because it's still doing the same pressure. So what you're doing is you're changing the flow rate, right? You understand that? So we're not changing the pressure. So what does the pressure determine? What does the pressure determine? The amount of pressure. It determines the force. So force is equal to how much air we're pushing against times the pressure. And there's a different formula for flow rate. So the flow rate determines the speed. The pressure determines the force. Don't understand the difference. Pretty important. So when we change these flow control valves, we're not changing the amount of force. What we're changing is the speed that we apply that force. But look at that. Look the way it's related. So V means this is a valve. This is V. This is a valve. So anytime we see V, we know it's a valve. Anytime we see M, we know it's a solenoid. What's this a symbol for, people? What does that tell me about this valve? Y'all have had fluid power. All y'all's had fluid power, right? What does that tell me about the valve? It's got a manual operator on it. And that's that manual override. That's the thing I was using, that little Allen wrench I was sticking in the side. That's a symbol. So that's the manual override for the valve. So I can literally shift the spool against the wad, against the solenoid. So the way this thing is laid out, and this is really, really standard, guys, is the way they lay it out is they come up with we call them actuator circuits. And what's really neat is we can look at the diagrams for the Festo line, and this is a standard, and we can understand this. So what we got is when we get a diagram, so this is the pneumatic diagram for the system. And notice what they do. Each one of these controls an actuator or something that acts like an actuator. And they start numbering them from left to right. And notice, so this on the right, this on the left, excuse me. This right here is that's the valves, right? I'm sorry. This on the right. Would be the first circuit. So notice the first circuit over here on the left starts with the number 1. On this, which is the second circuit, it starts with the number what? 2. This is the third circuit, so all the symbols start with the number 3. This is the fourth circuit, everything starts with the number 4. So if I go over there and I see a 4M1, then that means it's in the fourth circuit. Then the numbers are assigned from top to bottom. So notice the first solenoid we see is 1M1. So this is the first thing it sees at the power source, right? You understand? Then the next one is assigned what? 1B2, 1B3, 1B1, 1B2, but these all belong to actuator number 1. See how that works? Yes or no? And now so here, this is the pneumatics. Here's the second circuit. This is the vacuum generator right here. The first one that it sees from the power source is 2, because this belongs to circuit number 2, right? You understand. Then this is M, so this is a solenoid. And then they go from left to right. So this would be 2M1. Would be what? 2M2. This would be 2V2, because this is 2V1. That's the first valve. This is understand, this is a pressure control valve. This is 2Z1. What is Z? It's the gauge. And this would be the actuator. We have 2 pressure sensors on this. We have a pressure switch, which is 2B1, and we have a analog pressure sensor, which is 2B2. But I know it's a sensor because it's got a what? A B. Y'all understand this, okay? And then we move over to the next circuit. This is 3 because it's the third circuit that we encounter. M means it's a solenoid. This is 1 because it happened to be on the left. This is 3M2 because it's on the right? So they number from left to right. 3V2, 3V3, 2B1, 2B2, and of course the third actuator. And then we move over here. This is the last actuator that is controlled by this circuit. And we can bring up the diagrams for the Festo line, and they're going to be exactly the same. Everybody okay? So we got 2 power sources. So we got 2 drawings. This is the drawing for the what? For the pneumatic power source. And this is the one that is the pneumatic power source, by the way, establishes the numbers that we use. If it's not part of an actuator, then it gets a completely different number. So we've got, on this one, we got a photoelectric sensor that's not part of an actuator. We'll look at that in a minute. Are we okay? Yes or no? Are we okay? Any questions on this so far? So I'm going to run this off for you. So these are our sensors. By the way, I think they don't use diamond shapes. Let me make sure. Let's look. Yeah, they do. I'm sorry. I said diamond shapes. I was thinking motor controls. PLCs, your non-contacts are inside square. Are you okay? Motor controls are inside of diamond. These are the centers right here. So if we see this inductive, so what does an inductive sensor do? Anybody know? These are magnetic sensors right here. See the little trough thing I drew a while ago, which would be this guy right here. So this is magnetic. If we see this solid black rectangle, this means inductive. If we see these two parallel lines, it means it's a capacitive. If we see this, odds are it's in it. And here they use a combination. This is optical. This is magnetic. This is the symbol they use for ultrasonic. And this is normally open. This is normally closed. So what does an inductive sensor do? Has anybody used an induction sensor today? So what an inductive sensor does is it senses metals.
Senses metal.
Metals. That's all it senses, metals. This is what they put in the road. Those little things you run over to trigger the red lights. Those are inductive sensors. And what are they sensing? They're sensing the metal in your car. A lot of people don't understand that. So that's that big old loop out there. That's nothing but a big old inductive sensor out there. And when you pull up on that loop, that's an inductive sensor you're pulling. Go ahead, Jerry. What do you mean? It's an inductive sensor.
I'm just saying, when you said that, I said magnetic.
Yeah, but inductors generate a magnetic field, but inductors can sense magnetic field. So metal detectors, if you got a metal detector, that's an inductive sensor out there. We can design them to do we can have them linear inductive sensors, or we can have digital inductive sensors. Now all the inductive sensors on our lines are digital. Are we okay? Capacitive. Capacitive sensors can sense liquids or solids. They can sense gases too. So one of the methods that smoke detectors work on, they work on capacitive sensors. So we can design capacitive sensors to sense anything. So that means I'll show y'all some sensors. We can put one of the cubes on there, light it. I can put my hand down to it, it'll light it off because it'll detect that because I'm considered to be a solid, right? Optical sensors sense light. Ultrasonic sensors are going to sense distance. And then that's basically, these are our limit switches. This is a normally open limit switch. Y'all know the symbol for normally closed, right? We just move it over to the other side. Y'all okay? This guy right here, if it's got this and it's got this X through it, what's this a symbol for? Indicator. This symbol, where it actually comes in and has a mechanical connection between multiple contacts, this is a switch that we call a selector switch. See this little tiny trough right there? Anybody know what that means? This little tiny V right there? This means it's got a detent. And a detent means it holds the position. So you can actually feel a selector switch. When you move it, you can feel it fall into that detent and it'll hold that position. These are symbols for solenoids. And this little V that points toward each other, this is the symbol for the valve itself. So these would be the solenoids that are used to control the valve. So they don't give us the valve symbol, because what we're fixing to do is we're moving into the electrical diagrams, right? You understand that? So I don't need to see the valve. All I need to see is, I don't need to see that big 2-block, 4-port thing sitting there, 2-position, 4-port thing. All I need to know is that these are the 2 solenoids that do what? This would be for a single acting cylinder. Or I'm sorry, this would be for a spring return. So when we look at some of our diagrams, was that in there? No, this one don't have one. But some of our 2-position valves does not use a solenoid on one side. It uses a spring. So if it uses a spring to send it back, then we say that's single acting with spring return, or single solenoid spring return. All these are double solenoid. So here we use solenoids to push it in both directions. And then here it is right here. Yeah, so this one right here is a single solenoid with spring return. So when I energize this solenoid, it's going to push that symbol that way. When I de-energize this solenoid, it's going to push that symbol this way. On this one, when I energize this solenoid, it's going to push it that way. This one has to be de-energized. We can't energize these at the same time. If I energize them at the same time, what's going to happen? Nothing. It's going to stay in whatever position it was in, right? Because those 2 solenoids are going to be doing what? Pushing against each other. So on these, what we do is we de-energize this one. The valve stays in that position. So we don't have to leave these energized. And how long is it going to stay? Well, it's going to stay in that position until I energize this one and de-energize that one. What's nice about the Festo line is they use indicator cables. So the cables themselves have got LEDs in them that light up, and you can actually see these things switch. The Amatro line, they don't show you all that, so you don't see which one switches. You'd probably have to look at the output of the PLC and see what's on.
That D you saying on the other one?
Is that what we call a D10? Huh?
Everything between solenoids is represented by.
Oh, that little thing right there. That's the valve.
Yeah. So
now in pneumatics, they use that as the symbol for what I think we call it a butterfly valve. So that's a type of valve, and that's a true symbol in fluid power. But in the diagrams, we use this to represents the valve. So this guy.
it could be whatever's in between those.
Yeah, but that is the valve. This little symbol is the valve.
Right.
So that is the valve, but this is going to be for a spring, one that's got a spring return. Y'all understand? But we're looking.
Simplified drawing.
Yeah, because if they draw that whole valve in there, this is the electrical preamp. I'm not concerned with the valve. I'm concerned with what controls the valve. But we got to have something in there that lets you know there's something between those 2 solenoids. So that right there is representing the actual valve itself, the valve body and the spool. This is a normally open push button. We have a ton of those. This is the E-stop. Now this little symbol right there means it latches. So that means when you push it in, it latches. This is a symbol for a momentary contact push button. Now what's a momentary contact? That means you push it, and when you let it go, it changes backstage. And then this is the symbol for a relay coil. So it's quite a bit different than the symbol. This is the international symbol. So when we start looking at the electrical drawings, this is what we have. So this is the PLC. I don't know if I've got, I need a. So this down here at the bottom is the PLC. So this is the actual ports we hook up to the PLC right here. This 1L, this is power. So this will be 24 volts right here. And then this would be a momentary contact push button. This would be a momentary contact push button. This would be a what? This is the E-stop. It's a latching push button, and that has a detent, and this is another normally over contact push button. This is the terminal board that takes us between that actually allows us to go through a cable. We'll show you that in a minute. So what's nice about using a cable that's got connectors on it is that you can pull the PLC out without doing any rewiring. We'll show you that in a minute. Now this is the rest of the print. What's this? This is a magnetic reed. This says it's a magnet, senses a magnet. This says it's a normally open contact. It's only got 2 wires going to it, so this is a magnetic reed switch. This is a magnetic reed switch. This is a Hall effect. Why do I know it's a Hall effect? It's got 3 wires. 3 wires. Yeah. So notice the numbers are the same. I'm sorry. The output is 3. Right? You understand? I'm sorry. So this is the power coming in. So this is plus 24 volts. So if y'all had PLCs, somebody had PLCs? No? Well, when we have a circuit, what we can do, and PLCs run different. We call this L1 and we call this L2. Which one's positive, which one's negative? L2 is always common, but I didn't ask that question. I said which one's positive and which one's negative. We talked about this just a while ago. I established the common. So you establish what's common. So when I come over here to these switches, this is the common for the switches. This is the single wire, and so I've got positive run into every wire. So that wire right there is common to the switches. Okay. So that means on this one, this side right here would be positive. So here's my switch. Okay, so that means over here, when I go into my PLC, then the other side of that input has to be hooked up to negative. Okay, y'all understand that? That just happens to be for this situation right here. I could just as well do it the other way if the PLC allows. So the device that's hooked up to the negative in PLCs, we refer to this as syncing. When you take digital, this will make a lot of sense. And if you use a positive common, we refer to this as sourcing. And they should have talked to you about that in PLCs. Because you can buy different PLCs that either sync or source. So if you looked at what's nice about modular PLCs, if you were on one of the 504s over there, if you looked at the input module, it said syncing. So that means if I got a syncing input, my devices have got to be sourcing. So that means my devices are going to use a positive common, and my PLC is going to use a negative common. So here we have the common depends on what we're talking about.
It says syncing.
Yeah, syncing. S-I-N-K-I-N. This is sourcing. This is syncing. So that's the way they designate. That's the way they designate your inputs and your outputs. They say your outputs are sourcing. So it means if your output's source, then all your devices have got to be connected to minus, right? You understand? So a sourcing output requires a syncing load. Y'all understand? Which is common. This is common. So all our Siemens PLCs use syncing inputs and sourcing outputs. So it means all my loads, I'm going to use a negative common. All my switches are going to use a positive common. So if you got a syncing input, then your sensors have got to be sourcing sensors, right? You understand that. Now this only comes into play on DC. If we use AC, there's no such thing as syncing and sourcing because why? AC doesn't have a polarity. That makes sense. Everybody okay? Any questions? Yeah. So all these, we would say all these, if I hooked one of these, if I used a negative as my common on my push buttons and my sensors, and then I hooked up the positive right, this guy would work fine, but my PLC wouldn't see a 1 and a 0 because it's set up to see, it's set up to sync, right? It's hooked up to ground. Or not ground, it's hooked up to minus. So you'll see in PLCs, we don't designate ground. We're going to say minus or plus. And now we have commons on the input, and we have, so over on, in motor controls, we could have said, well, L1 is common. So what is common? Common is a wire that's connected between all the devices. So L1 could be considered a common, and L2 could be could be, and that's the way we do it in PLCs. We don't do it in motor controls, because motor controls we're dealing with AC. So AC we attach one, we reference to one line, and we call that L2. But in DC, we can have a positive thing that's connected to everything, or we can have a negative thing that's connected to everything. So right here, you notice on these inputs, what's connected to every one of them? Positive, right? You understand? Here's negative down here. Negative is not being used. It's available on the terminal block. It's not true. We got to have negative on these sensors right here. Why do we have to have negative on the sensors themselves? Because they're a solid state, right? And they have to be what? They have to be powered up. But only certain sensors are connected to the negative. Every one of these devices is connected to what? To plus. Everybody understand that? So since every device is connected to the plus, we would consider that to be common to the inputs. So that plus is looking for a what? It's looking for a minus. So that means a sourcing sensor has to hook up to a syncing input. If I had sourcing inputs, then I would have to use syncing sensors. Well, that's very, very important. Some PLCs allow you to set what's common. And we'll go and look at the Allen Bradleys. A lot of the Allen Bradley PLCs allows you to establish what's common. The Siemens PLCs are not, so you have to know that. So we have to figure out, we'd have to look at the diagram. Most of the time, we use syncing inputs and sourcing sensors. So, but if it gets voltage back, if you was looking in the memory, it would be a 1. If it gets no voltage back, if you looked in the memory for that input, it would be a 0. Now, which one's true and which one's false? Is a 1 true and a 0 false, or is a 0 true and a 1 false? Normal tendency is to say the 1 is true, but that's not true. It depends on whether you use an examine open. What's that? Is examine if open, like it goes like that? Or examine if off? No, how does that go? Examine on, examine off. You don't know what I'm talking about? So this contact, if we use one of these, this is an examine close. If you use one of these, this is an examine open. And there's 3 letters, I just can't get them. Yeah. So it's true if it's open, if the switch is open. Right, you understand? Here it's true if the switch is closed.
So what you saying? If it breaks, something breaks the back.
Right. If you looked at the memory, if it's normal DC power supplies for PLCs is 24 volts. That means if you got a 24 volt DC input, if this PLC, if the beam is not broke, it's going to get a 1 back. So if I look at that light down there, that light's going to be lit. There's nothing there on the input to the PLC. If I break the beam, the light's going to go off. Now, what is true and what is false depends on whether you use an examine if closed or an examine if open. So if you use an examine if closed PLC program, that means a 1 would be true and a 0 would be false. If you use an examine if open, then a 1 would be false and a 0 would be true. Because you're trying to detect when the symbol changes states, right? You understand? So if this was an examine open, I mean, if this was true when it saw a 1, then I couldn't detect when it changes states, right? You understand that? So that's what we're trying to do, is to detect when it changes states. So we have examine if closed. Y'all remember that? It used to be that was so dang complicated, and I couldn't understand why. So that's why if you use a normally closed push button, you have to use an examine open. And this got people confused because if you have a normally open push button, then you come over here and you draw it like that, but the push button is normally open. But it acts like when you press it, it changes state. So you got to change the state, right? You understand? So if I've got an E-stop button has to be a normally closed push button. And stop buttons are supposed to be normally closed. Because what you want to do, if you got an examine open, if you've got an examine if closed, right? You understand what I'm saying? If you're using a normally open contact for this, well, what would happen and it's your stop button? What would happen if the wire broke? You wouldn't be able to stop it. So your stop button is supposed to be a normally closed contact. Well, the problem if it's normally closed, right? You understand? If it's normally closed, then if we use this one, then I would be stopped all the time because this is true when it's understand. So what we have to do in PLCs, if I'm using a normally open, so normally in motor controls, if we have a stop, we use a normally closed. In PLCs, we use a normally open if it's a normally closed push button. Huh? No. It depends on whether you get a normally open or a normally closed push button. You mean to go get you each one of them? Yeah, you got 2 different times. That'd be awful if I didn't have that, right? So the stop is supposed to be a normally open. Well, this says examine if open. Right? You understand? So that means if I use a normally closed push button, it would never be true. So that means you understand. Yes or no?
That's okay.
So what the PLC gets back in the memory, so let's say it gets 24 volts. Then what we would get is inside my memory, I would get a 1. If we get back a 0 inside the memory that controls the PLC, we would get a 0. If I use an examine if closed, this would be true, this would be false. If I use examine if open, this would be false and this would be true. Okay, so let's say I use this, let's say I'm drawing in my PLC, I come over and I draw this symbol right here, and I use a normally closed push button. So out here I got a normally closed push button. Well, that means I got this is true. This guy sees this as false. So it says, okay, it's false. So that means before it runs, I would have to go in and I would have to hold my stop button in to make it run. Now, we don't want to do that, right? You understand? Because we're saying examine if it's true if it's open. But I'm using a normally closed switch. So if it's true if it's open and I'm using a normally closed switch, right? You understand? To make it work, I've got to press a normally open switch down, right? You understand that? So we see the advantage of doing that because it's nice in that I don't have to worry about normally open and normally closed switches. So if I use normally open switches, then I can use this one or that symbol, and it acts like a normally closed contact, even though the switch is normally open. Y'all understand that? So what we have to do, if I'm using a normally closed switch, I have to use this in my diagram. When I draw my diagram in the PLC program, I use the symbol for an examine if closed. So that switch is closed all the time. So if it's closed all the time, then this guy right here is true. And if you go over there and press it, then it becomes false. So what we're saying is, if you use a normally closed switch in a PLC, if the push button is normally closed, then you have to use a normally open symbol. But in motor controls, it looks right. In motor controls, it's got to be a normally closed switch, right? You understand? So the problem is it gets people that said motor controls confused, because they say, hey, the stop button's supposed to be normally closed. Well, see, motor controls, it's the symbols are all right. In PLCs though, it's not a switch, it's a logic, right? And when the switch is closed, it always gives us back a 1. When the switch is opened, it always gives us back a 0 in memory. And then depending on which symbol we use, depends on whether what is true and what is false. So if I use this symbol right here, then what's true? Well, if it closes, it's true. If I use this symbol right here, if it opens, it's true. Right? You understand? So I go out there and I use a normally closed push button out there on my PLC, and I use that symbol right there. Well, open is true. So it sees that it's false all the time. So the unit won't start. So now what do I have to do to make it run? I got to hold my stop button in all the time, because I'm examined if open. It's true when it's open, right? You understand? I want it to be true when it's closed. So if it's true when it's closed, and I use a normally closed switch, it's going to be true until we break it, right? You understand that? I don't know how else to explain to you guys. But the problem is, in a PLC program, if I use a normally closed switch, when I draw it, I don't use the normally closed symbol. I have to use the examine if closed, right? That makes sense. But we have a big problem in that on the 1100 PLCs over there, on the 1000 PLCs, all the push buttons are normally open push buttons. So that means when you want a stop button, you have to draw it as a examine if open. We have to examine if open. But the problem is, when you get out in industry, stop buttons are not going to be normally open buttons. And why? What's the danger of using a normally open button as a stop button? Huh? If the wire breaks, you can't stop it. You don't understand that. If the wire breaks and you over there, you can beat on that, and it says examine if open, right? Well, the dang thing's what? It's open all the time. So you have to close it to become true, right? You have to open it to become true. So it's kind of strange in PLCs. So and when you have a normally closed push button and you use that symbol, that gets people that said motor controls confused, because it says, wait, the stop button's supposed to be normally closed. The stop button's supposed to be normally closed, Rich. And I say, no. We want to use a what? We want to be true if it's closed. And this is the symbol for what we call examine if closed. This is a symbol if we say the other one is examine if open, right? I understand that.
Over here we got 2 stops. We got that big button.
Well, the big button is an E-stop. This is the one thing that the Festo line does not have. Now, the new versions, from what I understand, do, and it would be hard to add one. So, stops it. It don't remove, it don't kill anything, right? You understand? E-stop, when you push that down, so the stop button is a momentary contact. So that means I can, yeah. So the little button, that's a stop button. The big red push button is a E-stop button. So what does the E-stop button do? Stop the whole line. That's what it's supposed to do. Or maybe not the whole line, but it's supposed to, it might, like down at Mercedes, when they hit the E-stop, odds are it's not going to stop every plant, but that's multiple plants, right? You understand that? So this guy right here, what's happening here is you have this guy over here is called a what? Y'all read that up there? Reflector. So what happens, what does this guy depend on? This works kind of like a through the beam. So over here, the transmitter and the receiver are in one unit. So it transmits light. It comes over here. If the object is not that, then it hits this mirror or this reflector, and it reflects back. So we refer to this as a retroreflector. Now, what is a retroreflector? A retroreflector, if you look at one real close, it's made up of all these little triangles. And what happens is that if it hits at an angle, it'll bounce back at the same angle over a range. So what a retroreflector means is that your transmitter and receiver don't have to be perfectly aligned. If it was a mirror, what would happen? They would have to be perfectly aligned, right? You understand? So if my reflector was off a hair, then my return beam would go back over here somewhere. So a retroreflector is a special reflector. We see them all the time. They're on our street signs. So you can see that stop. If it was a mirror up there, because your lights would reflect over there, but that retroreflector, even though you're beside it, it still reflects back where? Towards you. These vests that you buy, they're retroreflectors. These reflectors you buy for your car. I've seen people put it on their mailboxes. When you live out in nowhere and you're on a road and you're trying to find your driveway, they'll put these retroreflectors out there. Y'all seen that? So they don't drive past, but they don't have to be lined up perfectly. Those are all reflectors on bikes. And you can look at them, you can see those little triangles in there, right? You pick them up, and that's what they are. They're retroreflectors. A lot of tail lights, they'll use the retroreflectors, but they use it for another reason, to spread the light out. So you'll see these all over the place. And you can look in there and see those little squares, and each one of those is a little tiny triangle, and it puts hundreds of them in there. And that way, and it's within a viewable angle, right? You understand? So when you get it right beside the stoplight, you can't see it anymore. Then we have a diffuse sensor. Diffuse actually depends on reflective light. So reflective light, the transmitter and receiver is still in one unit, but it actually depends on reflective light. So it reflects off the object. We'll go over there and see these. They're pretty obvious. Are we okay? So which one of them has the ability to have the longest range? Which would you think? What do you think, Alfred? Got three choices. 33%. Top one? What do you think, Eric? Middle? What do you think, Brad? Top one? What do you think? This, the light only has to go one direction on the transmitter to the receiver. This one would be half the range of that one, because this is not only going out, but reflecting all the back. That one up the top is really bad because it's depending on the color of the object. So how much light reflects back depends on the color of the object. So the diffuse sensor probably has the shortest range, which is some of y'all chose, but y'all understand why now, right? Because it's literally reflecting off an object. How much reflective light do you get back? No. So why does my shirt look blue? Why don't it look green? I mean, there's green light available out. We got green light, we got red light, we got blue light, we got all these different color lights. But why does that look like it's blue? Because that's the color that it's reflecting. It's absorbing the other lights, right? You understand? So what that means is how much light I get back at diffuse determines on the color that it's bouncing off of. So if the objects I'm sensing are black, that means those black guys are going to have to be right up against the thing, right? You understand? If it's a red light and I'm seeing a red object, then we'll get a lot of reflective light. If I got a green object, I get different lights reflected depending on the color. So diffusers probably have the shortest range depending on the color. These guys break the light. All these guys do is all they got to depend on is they can't be translucent. If they're transparent, then we got a problem. If they're translucent, then odds are we might not have a problem. It depends on where we set the threshold at. But through the beam on the diffuse, light has to go two directions. It's got to go out and it's got to come back. The only one where it don't have to come back is which one? Yeah, through the beam. So through the beam has the ability.
The deflecting object shows an object in the middle, and the beam comes out and hits that.
No, well, but it's not reflected. It's depending. So these two right here get 0 back if they detect it, right? You understand? Yes or no? These guys right here, this guy right here gets a 1 back if it's detected.
What about the bottom?
What about the bottom?
That's what I'm saying. The beam goes out and hits the deflecting object.
Not this one. You said the bottom one. When I say the bottom, this is the one that has the longest. This is the one that has the ability to have the longest range. So all these, the light has to go back and come back. On this, the light has to go out and come back. So that means that the light has to travel a longer distance, right? You understand? This right here, the light just goes out and don't have to come back. So which one has the ability?
So you're saying the light goes through the deflecting object?
It's not deflecting, it's detecting. Now I understand your confusion. The object that we're detecting. So the blue block is the object that we're detecting. This is the object we're detecting. This is the object that we're detecting. This is the object that we're detecting. Right? You understand? Here, where can I move my object at? My object could be anywhere in this range right here. Right? You understand? This has to be between this and the retroreflector. This, it has to literally have to bounce off the object. Okay, you understand the difference? Yes or no? Yes? No? Okay, so let's go over and find these. Probably the Festo line is the best place to go look.